Next up, we'll be continuing the theme of hearing about dense star clusters and integration of stellar dynamics therein in larger hydrodynamics.
Hello, I'm Yongseok. I'm a postdoc at Columbia University. In the morning, I was listening to the talk, and I imagined myself giving a talk here, and I kind of found myself like Steve Jobs or something. So I was like, okay, this is not good. Yeah. So yeah, I'd like to start by stating that how like star cluster community and galaxy formation communities are like dissociated with each other on a different levels. So here, my talk and my research is about like how to bridge those two communities on a very like technical level. So I'd like to touch on the technical side of that problem. So here, what I did is I integrated the drag and body simulation into hydrodynamic simulations. So drag and body is usually used for like solving star cluster and collisional gravities. So this is actually not the very this has been done before on a different level. So for example, they used here. They try to like use different more sophisticated time integrator to increase the accuracy of the gravity of star cluster. And here, AMUSE is a kind of framework. It's a kind of modular, so that we can like modularize all the like not just hydro, like gravity and hydrodynamic solvers. You can like choose whatever you want, and you can come up with a new simulation that can solve, that can like according to your taste. And here in this work, they used particle mesh gravity solver so that they can have more like local collision, more small scale, result more small scale gravity. And another example is like they use KETSU, which is for like black hole physics, like two-body interaction and three-body interaction. And like yesterday, actually, there is a new paper published which used the direct sum. But here, the problem that these examples are, their simulations are very limited in terms of spatial scale and also temporal scale. So they usually cannot exceed like 10 parsec resolution, 10 parsec box size, and more or less like less than 10 mega year simulation duration. So I brought some gravity solvers here. So there we can classify gravity solvers into two different types. One is collisional, and the other is collisional. Collisionless and collisional. So the problem with collisional is it's really very computationally expensive, but it's really important to resolve the physics of star cluster. So if I go into a little bit deeper, then actually to resolve like full star cluster physics, we need more than just direct sum method. So we need more like, also need time stepping, the sophisticated time stepping according to the gravity solver. And we need also two-body dynamics, like two-body interaction, hard binaries, or it could be like gravitational wave physics. So people use usually the regularization scheme for this. So, and this is the kind of motivation of my work. So this is the basic idea and assumption of my work. So which is about time scales and the temporal scales of simulations usually. So if you look at dark matter, stars in a star cluster, the major difference is the crossing time and relaxation time is way smaller in the star cluster compared to dark matter and stars in a galaxy, not in a star cluster. So we can think of them like dark matter and stars in a galaxy as more like just collisionless particle, and whereas stars in a star cluster should be collisional. So I assume that all the like physics that happens on a dark matter and stars in a galaxy as a quasi-static, so that I can use them as background potential. And we're going to solve the dynamics of a star cluster on top of that background potential, which saves us a lot of time. So in detail, so there's in simulation usually there's 4 players here. So dark matter, gas, and galaxy stars, which is not within the star cluster, cluster stars. And here in my work, in my code, we divided them by 2, which is collisional gravity, solved by collisional gravity, and the other is solved by collisionless gravity and collisional gravity. So we're going to solve dark matter, gas, and stars in a galaxy with the collisionless gravity, which was particle mesh method. And we're going to think of them as just background to the cluster, stars in the star cluster, and we're going to solve collisional direct n-body solution gravity for the stars in our star clusters. So this is the pipeline of our simulation. So we calculate basically full potential and the background potential without stars in the star cluster. And then we're gonna, while the hydrodynamics are being solved, we're gonna solve like here this direct n-body solution on GPU. So that happens in a like parallel level. So again, so we separate full potential and a background potential. So this actually saves a lot of time so that we can actually resolve the physics of star cluster in a live galaxy or even like in a cosmological context. So I'm going to show you some a series of tests. So here, this is about like robustness of our direct n-body solver. So we compared our simulation to n-body 6++ GPU code, which is really robust, known for robustness. So here, this is red line. Sorry. Red lines are our code, and the dark blacks are our reference. So as you can see, like we can resolve the core collapse very accurately, matching the n-body 6++. That's really good sign. And we compare our code to the just original ENSO. ENSO here is a hydrodynamic simulation without any sophisticated gravity solver. Then we can see that our code actually maintains its like gravity, the structure's integrity of star cluster, whereas ENSO here, they just explode, do nothing. But if we like kind of push our resolution to very extremely, then actually with just normal regular hydrodynamic simulations can actually maintain its shape, but we cannot resolve its like gravitational dynamical evolution with normal regular hydrodynamic solvers. So here, yeah, I'm going to show you this movie. So we actually implant our the star cluster at the center of the live galaxy here. Here. So on the left, this is our code, and on the right, this is our code, and on the left, this is ENSO, or the original ENSO. If you look at the star cluster here, then we can see that like it maintains shape quite well, but here it suffers from like the artificial gravity by the particle mesh code, which is implemented in the ENSO. And another example is that we implement this star cluster in the outskirts of a galaxy. Then here in just regular ENSO, it's just tidally stripped. right away, and you can see nothing interesting here. But here, with our code, you can see still like star cluster maintaining its form. Yet we can see some tidal stripping here. Yeah. And so that was my first paper about this, and we were trying to like move on to more scientific cases, build scientific cases. So first project that I did is we studied the evolution of nuclear star cluster in a life halo. So we implant the nuclear star cluster at the center of the life halo, life galaxy. And I have all the like star formation recipe and star stellar physics, like star supernova feedback here. So you can see that like we actually can form a lot of stars, star cluster from star formation around the star cluster, nuclear star cluster, and they actually merge into the nuclear star cluster here. And we can see nuclear star cluster actually evolve by March. And at the same time, there's in situ star formation happening inside the star cluster. So this paper is about like how to interact how the star formation within star cluster and mergers actually interact with each other. For the sake of time, I'm gonna show you some like another project led by my students. So Minyoung here is actually there, is working on formation of ultra-faint dwarfs at high redshift. So this is basically cosmological simulation, cosmological zoom-in simulation targeting this ultra-faint dwarf. So you can see some, but here we didn't really use star-by-star physics yet, which is like individual stars. So I have some movie here. So this is actually stars. It's gonna be here. So this is formation of stars within the halo, and this is gas. This is the total mass, I think. So this is a cosmological simulation. So we can resolve like collisional stellar physics in the context of cosmology. And another interesting project we're trying to do is, it's kind of slow here, but we just prepare the isolated galaxy and we just leave it grow. Then we're going to actually see nuclear star cluster forming within the galaxy. And actually we have some like black hole formation recipe and stuff. So our final goal is how the black hole actually form within the star cluster and how the black hole actually evolve by like runaway mergers and stuff. This is an ongoing project. And lastly, this is something that I'm working on right now. So for the physics of star cluster, the star-by-star physics is really important, which is like we have to resolve individual stars in the simulation. So, and I'm interested in like high redshift. So POP3 stars and POP2 physics is important. So here, this is EOS, something called EOS simulation, done by Cayley at Harvard. And here we have 10 different metals and 6 bands radiation transport based on their energy level. So we can resolve all these stuff so that we can produce like POP3 stars and POP2 physics quite well. Yeah. So I am working on this project, and there's a lot of possibility in this work. So I'd like to have some input and collaboration opportunities here. So I'm going to leave my last slide here, and I'll take the questions. Thank you.
Victor, why don't you ask your question while you set up the discussion section?
So very quickly, so very nice, very interesting work. I think it's an important direction. However, the test that you showed on the coherence of the star cluster in the new ENSO-ABIS implementation, it seems to me that it's more about the force accuracy rather than the ability to resolve the collisionality, right? So if I increase the force accuracy, for example, if I use a tree method instead of a particle mesh, I will also see that the cluster remains more coherent. I don't think it has to do with the ability of resolving the collisional dynamics in the cluster. Now, what's your comment on that?
So it's not just about like resolution. So we actually have like, so yeah, in terms of mergers of stars or any collisional dynamics, we have to use like regularization tools, schemes. So we have that. So we used a slow down regularization algorithm done by Wang, which I think quite robust. So we can resolve like at least 2-body, 3-body, and quadrupole quite consistently.
Yeah, no, I fully believe you. I'm just saying, the test that you showed is really more about force resolution and force accuracy. Anyway, we can
Yeah.
Take it away. Now have our discussion section.